Well, hello, physical science class. Again, this is an interesting time in which we're having to find some new ways of interacting with one another, and we're trying to do that through video lectures, through PowerPoint. So let me know if this works for you guys, and let me know if you guys have any questions or any clarification on anything that I talk about here today. We're going to be jumping into chapter 16, talking about the atom. We've spent a lot of our class time up to now. I think the very beginning we dealt with some chemistry, but for most of the year we've been dealing with physics subjects. So in these last few chapters we're going to be talking about together, we're going to be dealing with chemistry a little bit more again. So chapter 16, discussion of the atom. We'll be looking at the atomic model to start. The atomic model is a description of the atom. It's scientists' attempt to give a workable model, a description of how they think material in the physical universe is made up. And models, by their very nature, have to be workable. They are trying to provide usable answers to questions they're asking. And we're going to begin here by talking about the development of the atomic model, because what we know today about the atom is not what has been known over the vast amount of time in which people have considered these ideas. So we'll be talking about the development of atomic models as a historical perspective. We're going to be looking at the development of this over time. And the book goes through this pretty well. I might include a couple of people that the book doesn't give as much description about. So there might be a little bit of difference between my slides and the book, but between the two of them, you should have a pretty good, at least beginning understanding of the historical development of understanding the atom. So the model of an atom, an idea of what it looks like, a working representation is what we're after. We're going to be surveying the historical development of the atomic model, which is analogous to that which Luke the historian was doing as it relates to the history of what Jesus Christ did when he came to earth. Remember, Luke at the beginning of his gospel sets out to provide an orderly account of the events regarding Jesus' life. And so you almost get the idea that he did the work of a historian, talking with and interviewing various people, and then including that in his gospel account. So we're going to be doing that kind of work, but instead talking about the development of the atom rather than what Luke was doing. He's talking specifically about Jesus. So early atomic models, the earliest descriptions that we have comes from Leucippus and Democritus' idea near around 400 BC. And they put forward the idea that objects can continue to be cut into smaller and smaller pieces until you finally get to a piece that can no longer be cut. And they called that the atomos. Meaning not or un, and tomos meaning to cut. So the atomos, or as we know it as the atom, it was a word that was originally from the Greek, just meaning uncuttable. And they described this as the smallest particle. Now that was only a philosophical idea. There was no scientific knowledge necessarily. There was no microscopes. They couldn't look at anything on that kind of level. So it was just a philosophical idea that all things are made up of small particles of that very same thing, and eventually you get down to a particle that cannot be cut any further down. Now that idea, though, is rejected by Aristotle, who argued that matter is continuous, and Aristotle's influence is so great that for nearly 2,000 years, his influence regarding the state and nature of matter holds. And so we have this long period of time in which people disagree with Democritus's philosophical idea that all of matter is made up of uncuttable particles, which is a really fascinating part and understanding of history. Understand this: people who sink all of their trust into science have problems on their hands, because science itself has developed and changed its theories over time. Remember, we're just working with workable models, which will be influenced by further scientific development. And even the things that we know about the atom today might be shifted and changed over the next few years. Who knows, as further developments come out. So you're going to note here with me that we have this huge period of time in which scientific inquiry is barking up the wrong tree. They're not tracing us out the right direction. And yet, meanwhile, scientists of the day, people who were very informed and intelligent, would have laughed you out of the discussion if you said that you believed and agreed with Democritus's idea put forward in 400 BC. They would have laughed at you during those intervening years. So recognize this about science. All right, so evidence began to emerge that Aristotle's model of matter was incorrect, and chemistry pointed to the existence of atoms. So now we're starting to get to some actual scientific inquiry that's backing up the philosophy of Democritus. And perhaps one of the most important characters to this story, the unfolding drama of the atomic model, is that of John Dalton. You see his year here of 1803. He framed the first experimental model where he was weighing various substances, and he assigned some relative masses to the elements and was able to determine that atoms of different elements form compounds. By these differing masses and ratios, he determined that each element or different thing had its own distinctive mass. And his model is called the core envelope model. You can see this in your reading. After him comes along Joseph Thomson in the 1890s. Now, at this time, they had developed these things called cathode ray tubes or vacuum tubes, where they would insert a gas inside of a vacuum chamber, and they would put electrodes on either side of it, and they would notice that they could pass a current of electricity through that gas. And so Joseph Thomson is studying these effects, and he realizes and sees, obviously, that light comes from one of the ends, the end that was referred to as the cathode end. He noted that cathode rays were affected by magnets and electricity, but not gravity. So he saw these rays are coming through the tube, and as he brought magnets and various electrical sources near it, he could deflect the angle of these particles that were coming through the vacuum tube. And he recognized that normally, otherwise, gravity didn't have enough force to pull it down, but magnets and other electrical forces would deflect the flow of these cathode rays. And he decided that the cathode rays were negatively charged, and he calculated their charge to mass ratio. And from this, he found that every element that he tested emitted these cathode rays, which he then came to term corpuscles. But we now know them as electrons. Somebody else proposed the word electron instead, and that one stuck rather than corpuscles. But he called them corpuscles. We know them as electrons, negatively charged particles. Now, Thomson's model, this is, again, when you're modeling something, you're usually trying to make use of some analogy, something that you're used to, and using that analogy to then describe something about the world around you, right? So, like, if I'm eating something new and it's a meat of some sort, and it does kind of somewhat resemble chicken, I'll say, hey, it tastes like chicken. We've heard that kind of analogy made often. Well, something that Thomson was very familiar with was plum pudding. And as he thought about the atom, he put forward the idea that atoms are made up of some sort of positively charged, substance that has these negative pockets in it. And that's the way he described the atom, that the atom is made up of a positively charged substance that had these negative pockets. And those are kind of like the plums in the plum pudding. Or for us, we might say that it looks more like a chocolate chip cookie, where the chocolate chips are these negative particles, or what he called corpuscles, which we refer to as electrons, and the rest of the area of the atom was made up of a positively charged substance. It's called the plum pudding model. Like I said, it looks a little bit more like a chocolate chip cookie, maybe to us Americans. We're more familiar with that than we are plum pudding. The electrons are in a positive gel-like substance. The electrons and the positive substance cancel out. So he said there's enough positive charge within the substance to balance the negative corpuscles and the negative electrons that are present, so that the net charge is zero, but it is arranged in this fashion. Electrons can be removed from it. Now, what do we know now? What do we now know is part of the atom but's missing from Thomson's model? Well, he's familiar with cathode rays, but he referred to those, remember, as corpuscles, which we refer to as electrons. So he was dealing with electrons, but notice what's missing here is any understanding of the nucleus. Along comes Ernest Rutherford, who discovers the proton, the positively charged particle, subatomic particle. In 1910, the alpha particle experiment, he aimed alpha particles at a thin gold foil. these alpha particles were relatively heavy and positively charged. And his model looks something like this. There's a picture in your book that I think is even a little bit better than this one. But he had a little device that was set up that just had a radioactive material, and he was able to shoot alpha particles out of this at a very, very thin piece of gold foil. Now, he used gold because it can be, it's so malleable, it can be hammered into very, very, very thin sheets. And so he makes a very, very thin sheet of gold foil, and he shoots these alpha particles towards the gold foil. Now, his purpose is to determine what happens when these protons hit the gold foil. And he's assuming that they're just all going to travel straight on through the foil here, because they're just so massive, and this is just going to go right on through. But what he, and for the most part, that's what he finds. He's got somebody who's looking at this, and they're counting the number of little bits of light that shine on this material that's all the way around here. And by the way, that person's name was Geiger, and we get the Geiger counter from that, which measures radiation. But anyway, so he's counting these little specks of light, and they're noticing that the vast majority of particles are, sure enough, coming straight through. But the oddity that they discovered was that there were a few that were deflected, like this, but then there were even fewer, but there were at least a few that got deflected almost straight back from the direction from which it was coming, which made him to start to wonder exactly what is the makeup of the atom. So he has a zinc sulfide screen is what this is made of, and these alpha particles being slightly deflected, but then other ones that are being deflected. So a few alpha particles bounce back completely, while most of them pass through the gold foil. And so Rutherford concludes from this that atoms have a dense positive charge, the proton, and atoms are mostly empty space. So he's saying the reason why these alpha particles are just flying right through the gold foil is that, for the most part, the atom is made up of mostly empty space. And he's absolutely right. And so he puts forward the model that the positive charge is not made through a gel-like substance throughout the entire atom, but is densely compact in a central nucleus where the protons are found. Proton being 1,800 times as massive as an electron. Electrons are somewhere away then from the nucleus. And so this is what Rutherford puts forward, the nucleus and these protons being found there. So what do we now know is in the atom but was missing from Rutherford's model? Well, he described protons and electrons and the nucleus, so it's number one here, right? Neutrons. He didn't do those. So along comes James Chadwick, who discovers the neutron. According to Rutherford's model, there's not enough mass with just a proton and an electron. So in 1932, Chadwick discovered a neutral particle with almost the same mass as a proton. So proton and neutron are almost the same mass. They differ in about the amount that if you add a proton to an electron, you get roughly the mass of a neutron. There is a slight difference there. What's sometimes referred to as the mass defect between a neutron and the mass of a proton plus an electron. So a neutron is almost like the mass of a proton plus an electron. But in 1932, Chadwick discovers this neutral particle that is almost the same mass as a proton, because the electron is like almost 1,000 times less massive than the proton. So he called it. And then from there, a couple of other people come into the picture. Niels Bohr discovers energy levels for electrons. He started to ask the question, where are the electrons? Why don't the electrons just fall into the nucleus? Don't the protons attract them in? And in 1913, he engages in some spectroscopy experiments, and he argues from those that electrons give off exact amounts of energy by moving only in restricted steps from level to level or orbit to orbit, that they're quantized. And from this, he develops this idea of orbitals for electrons. That electrons are in different orbits, and they might jump up or fall back from different energy levels. And he was able to see through the spectroscope different discrete lines of color, which then he correlated with these various levels of energy, the lowest level being ground state. And so his model of the atom is referred to as the planetary model of the atom. And a lot of times you'll even see these pictures still around the internet, where you've got the nucleus and you just see these electrons. traveling around in like orbits around the nucleus, maybe semicircular orbits. And that's kind of the way that Bohr was looking at things. And again, this gets us even a little bit closer. He's trying to describe where are the electrons found in the atom. Again, these are just a couple of details regarding the spectroscope, and these different elements being heated produce different sets of wavelengths, which act like a fingerprint to identify elements. You can actually burn different elements and see different colors, and again, this is an indication of the location of the electrons around these elements. And by the way, this is the chemistry that's behind fireworks. You get different colors in fireworks from different metals being burned, being excited, and these electron levels being excited as a result of that. And you get these different colors. So there are 7 principal energy levels, and each level can hold more than 1 electron. Bohr's model works well only for atoms with 1 electron, but forces between atoms are not the same as forces within atoms. And for this reason, some other scientists come into the picture to further develop the atomic model. De Broglie's hypothesis is that all particles act like waves, and the bigger the particle, the smaller the wave. The waves are only significant for very small particles. But notice, we're talking here about subatomic particles, very, very small particles. So if that's the case, whenever you get to this very, very small particle, he says they act more and more like waves the smaller they are. And so his work, combined with Heisenberg, who develops the Heisenberg uncertainty principle, said that we can know where an electron is or where it's going, but we cannot know both at the same time. In other words, the more you know about the location of the electron, the less you know about where it's headed. Or, said conversely, the more you know about where the electron is headed, the less you know about its location. It's kind of like the dot on the fan blade. If you can locate it specifically, it is right here, you might not be able to tell which direction it's going. Or if you can tell the general direction in which it's going, you can't tell exactly where it is at the moment in which you're observing its motion. Like, it looks more like maybe a circle, right? You know what path it's taking now, but you don't know exactly where it is. But if you stop the fan blade and you just look at the dot, you don't know where it's going. So Bohr's precise, like planet-like orbits become replaced with the idea of orbitals, which are shaded regions. They're mathematical probabilities of where we might find an electron. So it's a region, it's kind of like a region of density, where they're showing electrons should be found somewhere in this area. And they look something like this. The neon atom, this is a depiction, again, the quantum model of an atom. This is a neon atom having 10 protons and 10 electrons. And the 10 electrons are being located within these regions called orbitals. Each region is depicting the mathematical probability of locating an electron. And you note here that you've got two spherical orbitals. This one here, which we refer to as 1s, and then this one, which is referred to as 2s. And then this guy, these figure eights, you've got a figure eight there, a figure eight here, and then a figure eight here. You see there's one on the x-axis, one on the y-axis, and one on the z-axis. So we've got 2 spherical orbitals, and then you see you've got 3 like figure eight orbitals. And each of these orbitals can hold up to 2 electrons. So 2, 4, 6, 8, 10. So the 10 electrons that you find around neon are actually found in these kinds of locations. And remember, each of these orbitals depicts where 2 electrons might be. So somewhere in this x orbital that looks like a figure eight, there are 2 electrons, and they are buzzing about somewhere in that region. And the more that I know where it is, the less I know where it's headed. And if I know where it's headed, the less I know where it is. There's a pretty cool video here at Khan Academy that you can check out if you want to look a little bit more into the history of atomic chemistry. All right. Well, that brings us now to section B in the chapter, looking at the orderly. Atoms are made of 3 principal particles, which we've already been introduced to through our history of the atom: protons, neutrons, electrons. Protons are located in the nucleus with a mass of 1.6726 times 10 to the negative 27th kilograms. So they're very, very small. It's a single positive fundamental electrical charge, +1 E. It is stable. So remember, it's a positive charge. It has a positive charge, which is balanced by the electrons. But first we look at the neutron, which is located in the nucleus. It has slightly more mass than a proton, as I said earlier. It has the same mass of a proton, pretty much a proton plus an electron. And it breaks down into a proton and an electron when outside of the nucleus. I think it's within something like 15 minutes or something. If a neutron's left to itself, it will break down into a proton and an electron. An electron occupies a region around the nucleus and has a mass of roughly 1,000 times smaller than that of a proton, about 9.11 times 10 to the negative 31 kilograms. So electron is much less massive than a proton, but it has the same amount of charge as a proton, just negative rather than positive. And it is responsible for chemical properties of an atom. It is the arrangement and number of electrons that engage in chemical reactions. Now, the atomic number, each atom has a distinctive number of protons in its nucleus. And the number of protons in the nucleus tells you what element we're looking at. The atomic number is abbreviated with a capital Z. If it's neutral, there are also the same number of electrons present in the atom. So the Z number is the number of protons. If it is a neutral atom, that means that the number of electrons has to balance the number of protons. So if the Z number is 10 and it's neon, then neon, when it's neutral, also has 10 electrons. If you remove or add electrons to an atom, it's still the same element because the element is defined by the number of protons in the nucleus. If you change the number of protons in the nucleus, you change to a different element. Okay? But the number of electrons can change and it still is the same element. So neon could possibly still have 9 electrons if it lost an electron. But it'd still be neon. But if neon loses a proton, it's no longer neon. And we find these all in the periodic table. Now, elements can have different numbers of neutrons in the nucleus. So the nucleus will have, for each element, will be a distinctive number of protons, but you can have different numbers of neutrons in the nucleus. And these are then referred to as isotopes. Now, the mass number of an element is found by adding the number of protons with the number of neutrons. Remember, electrons are 1,000 times less massive than a proton, so they really don't influence the mass of an atom. It's really just the sum of the protons plus the neutrons. And that's denoted with a capital A. Now, when we identify isotopes, we name them we give their name followed by their mass number. So, for example, you've probably heard of C14 or carbon-14. It's usually the thing that a lot of paleontologists and stuff utilize to describe the dating of things. They try to date things off of carbon-14, which, by the way, is notoriously problematic. But we're not talking about that here today. But carbon-14 is, again, a particular element with a certain number of neutrons within the nucleus. And so you can then look at the different weight of, for example, of oxygen. Here you've got oxygen 16 versus oxygen 18. 18 would have 2 more neutrons than oxygen 16. And so one is more massive than the other. Now, atomic mass units is just approximately the mass of a proton or neutron in the nucleus. The atomic mass of an element is determined by finding the average mass of its atoms in nature. So remember, we saw that oxygen could have 16 or it could have 18 as its total mass. So if we're asking, well, what is the mass of oxygen? We have to take all oxygen as it is found in nature, and then we determine how much of each type of oxygen is found in nature, and then do an average mass from that, and to determine then what the atomic mass of that element is. So, for example, nickel on the periodic table is number 28. That means, remember, that 28 is its Z number, indicating the number of protons that are found in the nucleus. And remember, if nickel is neutral, if it has no charge on it, either positive or negative, that means it must also have 28 electrons in its ground state. But notice the number that is below nickel here, this 58.69. That number is derived, remember, from adding the number of protons, which would be 28 for nickel, plus the number of neutrons. But remember that nickel could have various forms of nickel that have different numbers of neutrons. So how do they get to this 58.6? Well, again, we can look at this 58. So 28 plus what equals 58? Well, 30, right? So if every thing that we found of nickel was always a mass of 58, we would just have 58 down here. But instead, it's 58.69. So how do we get to this 0.69? Well, there must be various forms of nickel, or isotopes, that have different numbers of neutrons, meaning that there might be nickel 59, there might be nickel 60, there might be nickel 57, and then there might be different amounts of each of those types of isotope. So all of those are then averaged together to give us this number of 58.69. All right, so let's talk then about the electron arrangement in atoms. Remember, we learned about these energy levels that were discovered through a bunch of different scientists and their contributions to the scientific model of the atom. Energy levels refers to the location of electrons relative to the nucleus. Lower energy levels are closer to the nucleus. Higher energy levels are farther away from the nucleus. So higher energy levels can hold more electrons, but the ground state is the lowest possible energy condition. So atoms like to sit at ground level as much as possible, where the electrons are as close as possible to the nucleus. We also learn a principle which you'll learn more about when you get to chemistry, but it's called the octet rule, which means that there's always at the outer highest energy electrons is the magic number of 8, or 8 electrons that are involved in bonding with other elements. And this is where chemical reactions take place. It's with the electrons interacting with other electrons from other. This brings us to the third section of the chapter, the nuclear atom. If there are too many or too few neutrons, the nucleus becomes less. Nuclear chemistry, then, is the study of change that occur in atomic nuclei. Now, whenever we're talking about chemistry in general, we're usually talking about the interaction between electrons with the rest of the with other atoms and their electrons. But nuclear chemistry is the study of changes that occur in within the atomic nucleus. So nuclear radiation are rays and particles that are emitted by unstable nuclei. Henry Becquerel discovered nuclear radiation and activity. Alpha particles are composed of 2 protons and 2 neutrons. Beta particles are free nuclear electrons. Note here, we don't think of electrons being in the nucleus. So where's this coming from? Well, it's unstable neutrons that are they're splitting apart into a proton and an electron. And the electron then flies out of the nucleus, leaving behind a proton there in the nucleus. So it's like a neutron dissolves into a proton and electron leaves the nucleus. That's called beta radiation. So alpha particles are 2 protons and 2 neutrons going out of the nucleus. Beta particles are just the electrons leaving from a neutron that's split apart into a proton and an electron. And then gamma particles consist of just electromagnetic waves. So it's not a particle at all, it's just a wave of energy. So we have alpha, beta, and gamma radiation. There is no electrical charge on gamma particles. So beta have a negative charge, alpha have a +2 charge. Gamma radiation has no electrical charge. So here is just an illustration of radiations. Note here we have a radioactive source, and it's going through some beam-forming shielding to make sure that the beam, you see this is a little bit smaller and this is a little bit smaller yet, just to make sure that our beam is pretty much going straight this way. Then there's some charged plates that are applied here, both a negative and a positive plate. And you'll notice that the gamma radiation is the stuff that just continues traveling straight because it's unaffected by the charge of this plate because it's just energy, it has no charge to it. But beta radiation, because it has a net negative charge, is influenced by these plates such that it's deflected upward, whereas alpha radiation is deflected downward. Now note here that beta radiation is more strongly influenced by this charge, partially because of its less mass. It's able to be deflected easier than the alpha particles, which just have more momentum in traveling in the direction that they are. But you kind of see then the difference here between gamma, beta, and alpha radiation. So there are three types of nuclear decay: alpha decay, beta decay, and gamma decay. Gamma decay happens when the nucleus sheds excess energy by emitting a gamma ray. So we go from an excited nucleus to then just all of a sudden energy leaving from the nucleus in the form of gamma radiation. There is no change to the atom except for reducing the energy that is present within its nucleus. Remember, the same number of protons, same number of neutrons. Nothing's changed with the number of protons or neutrons in gamma radiation. There's just been energy that has left the nucleus. It is very penetrating and very damaging. Gamma radiation is the strongest form of radiation, much further penetrating than alpha or beta. Now, alpha decay happens when the nucleus loses 2 protons and 2 neutrons, and this forms an alpha particle. So you think of 2 protons, 2 neutrons. It's pretty much like a helium particle coming out of the nucleus. The remaining atom is now an isotope of a different element. Remember, I told you that the element is determined by the number of protons in the nucleus. So if we change the number of protons that are in the nucleus, we've actually changed the element. That's what happens in radiation. Radioactive decay means that there are protons, and in this case neutrons, leaving the nucleus, which then actually shifts the element down 2 steps. 2 protons down, it changes the element 2 steps downward. So it's now an isotope of a different element. So it's a different element, it's a different isotope because remember it has a different number of neutrons as well. It gains electrons and it becomes helium. That's the alpha decay that's gone out from the element. It now gains electrons and it becomes helium as it leaves. And this is easily stopped because it is an actual part to be stopped. So here's an example: uranium-238. Through alpha decay, we notice here that we start with uranium-238, which has 92 protons, and then 92 plus whatever to come up to 238 is the number of neutrons, which would be 146 neutrons. So 92 plus 146 equals the 238. So this is uranium-238. It has 92 protons and 146 neutrons. If it goes through alpha decay, which uranium is apt to do, we have a helium atom that leaves the nucleus, which means that 2 protons leave. So we go from 92 to 90, and 2 neutrons leave, going from 146 to 144, which changes then the element. It's no longer uranium. It's now thorium-234. And from this, there is a helium atom that leaves, but there's also EM energy in the form of gamma radiation. So beta decay is when a neutron changes to a proton and ejects a high-energy electron, a beta particle, or a free electron. The atom becomes an isotope of the element because through this, the proton, that neutron splits into a proton and an electron, and the electron leaves the nucleus, leaving behind a positive charge. So it used to be a neutral charge. It was a neutron. It splits into a positive and a negative, and then the negative leaves the nucleus, leaving behind a net positive charge. So it's actually become a new element and a new isotope. And again, though beta decay is also easily stopped, it's not as easily stopped as alpha decay, because remember, that's like 2 protons and 2 neutrons, a much bigger particle. This is just a very excited electron, but it is still stoppable in a way that much more stoppable than gamma. So it could look kind of like this: thorium-234, which we left off for the last time. If this now decays through beta radiation, what happens is we have the 90 protons, 144 neutrons. Well, 1 neutron splits into a proton and an electron. So we go down 1 neutron, but note here, the protons move up 1 because we get a positive and a negative particle from that neutron that's split apart. The negative particle leaves through beta radiation, but it leaves behind a positive particle, which is a proton. So we actually go from thorium-234 to protactinium-234. Note it's 234 still because that proton that neutron has now become a proton. So now we have 91 protons and 143 neutrons. And again, there's gamma radiation that is removed as well. This is an image just showing a radioactive source, and alpha radiation can be stopped by even just a sheet of paper. So alpha radiation, note here, can be stopped very, very simply. Aluminum foil is enough to stop beta radiation. But note here, this last line, gamma, goes right through the paper, right through the aluminum foil, even right through here a chunk of concrete until it hits this lead. Now, they do use concrete to shield radioactivity, but usually has to be very, very, very thick in order to provide protection levels. But lead does a fantastic job at shielding against radiation. And this is why if you're getting x-rays and stuff like that, they usually put some sort of lead thing over your body where they don't want to take any sort of scans or x-rays, so that way you're not receiving radiation to parts of your body where it should not be. So smoke detectors use americium-241, which is a radioactive element. Smoke disrupts the current flow, setting off the alarm. Now, I'm sure you've also heard of nuclear bombardment reactions instigated by man, which release far more particles and energy than nuclear decay. There's a collision of particles, and what makes it even more strong is whenever we can cause a chain reaction to take place, where we make a large nucleus unstable by striking it with energetic free neutron, and then start a chain reaction in which that particle splits apart an atom, which then releases other particles and split apart other atoms. And these happening in massively quick amount of time, where mass is then converted to energy. We remember the famous equation by Einstein, E equals, can you complete it? mc squared, right? Where mass here is being converted to energy. And when that happens, it happens on the basis of this equation. The c here is the speed of light, which is a very, very large number. And that speed of light being squared times mass. So recognize here a huge amount of energy coming out of mass being converted to energy by this ratio, mass times the speed of light squared. And this is what's behind atomic bombs and nuclear power plants, right? The only difference with the nuclear power plant is that they're controlling the rate of that reaction in a way that an atomic bomb is not meant to control it. It's meant to allow it to spiral out of control in a very, very large way in order to cause a massive explosion, lots of destruction. Nuclear power plant is trying to control that reaction so that it doesn't get out of control. It's supposed to be kept under a certain amount. But again, the same science is behind this. We're generating energy through mass being converted to energy. And then there's nuclear fusion, which produces even more energy than nuclear fission. As a matter of fact, the hydrogen bomb is a bomb that begins with a fission reaction, just like the original atomic bomb, but then that fission reaction provides enough energy to then begin a fusion reaction, which produces even more energy. So the hydrogen bomb is even more destructive than the original atomic bomb. But there's a lot of research being done for future energy generation around the subject of fusion, nuclear fusion. And in the book, I think at the very end of the chapter, you can see a picture there in which a description is being given of a company that's pooling resources in France to develop some nuclear fusion devices. They said something about in 2020 so this year they're supposed to be doing some things with that, and maybe in the next 15 years or so they'll have it actually producing energy. Anyway, they're working towards that. Maybe some of you will be involved in this field someday. Hope you guys have a safe rest of this week. Do the homework as assigned in iGrade, and I'll see you guys soon. Thanks so much.